Thank you very much. I'm very glad to be here for my first visit to India. So before we start talking about thermal management solution, let me introduce the company. So GM Huber Corporation is one of the largest privately owned company in the United States. We have, as you see here, 3 main business units. They're not related to each other in the application. So first one is CB Kelco, and these are producing some food additives. The other one is Huber Engineered Wood, and these produce wood sheets for the housing industry in the United States. And the last one is Huber Engineered Material. So Huber Engineered Materials has, again, 3 main business units. The silica business was sold to Evonik in September of this year. So we have only 2 now. One is the ground calcium carbonate, and the other is fire retardant additives. So I'm working for the fire retardant additives, and therefore, today we'll be talking more into details about this business unit. As you see here, for the fire retardant additives, we have 4 production facilities in the United States, in North America, and we have 2 in Europe. So in total, 6. We have 2 R&D centers. One is based in Fairmont, close to Atlanta, in Georgia, and the other one is in Bergheim, Germany, and that's where I'm coming from. Now, sales and technical support, we have global office worldwide. Wanted to show this slide to tell you a little bit about the strategy of Huber. As you see, the first part to the left, growth is very important, and as you see the acquisitions, the last few years, Martinswerke was acquired in 2016 in February. So we're almost 2 years part of Huber, and we were operating under Albemarle. Albemarle is also an American company producing halogenated flame retardant and catalyst. So now we're more working with halogen-free flame retardant within Huber. Huber also acquired in 2015 Sapphire. So these are phosphorus nitrogen flame retardant, work for polyamide, epoxy, and others. They acquired the ATH business from Almatis in 2012, and Chemarc, which is smoke suppressant, mainly for PVC. So to go further, this is our facilities in Bergheim, Martinswerke. We mainly produce mineral flame retardant based on aluminum hydroxide, fine precipitated and ground and coated, and Alumina, which are specialty product based on aluminum oxide. As you see here, we're very close between Düsseldorf and Cologne. Around 500 people are working there, and you see the very nice image. We celebrated our 100-year anniversary in 2014. So that's really company with history. Okay, this is very standard energy quality ISO certification. A little bit more details about the product portfolio. As I mentioned, mainly we do flame retardant, halogen-free flame retardant, and these are fine precipitated ATH. We're the global leader in production of fine precipitated ATH. We have ground ATH, we have low viscosity grades, we have magnesium hydroxide, we have surface-treated magnesium hydroxide, and as I mentioned, Chemarc and Sapphire. The other parts, we produce specialty product, and these specialty products are based on activated and calcined aluminum oxide. So we sell for refractory ceramic, but we do some development where we can apply special filler for the thermal management, and I'll talk more into details about the technical aspect. We do have some other product used as matting agent and some agricultural carriers application, and these are organic polymers. You can use them for paints and other additives. So before we start talking about the thermal management, I would like to show an overview showing the product we have as flame retardant. I have Mr. Mario joining me from Germany, which is a technical person, has been visiting India for several times. We have also Sharda Enterprise, our distributor in India. So please, if you have any question regarding technical question, flame retardant, talk to us. So first one are the fine precipitated ATH, aluminum trihydroxide. We have different grades. So Martinal is the trade which we produce in Germany. Hydral is produced in the United States. Main application is wire and cable application. Now the other one are the coated fine precipitated ATH, so marginal coated, main product 104, 107. We offer several coating depending on the polymeric application you're using, and the high mod are the product produced in the United States. We do have ground ATH and marginal ON products, and the other are produced in the United States. So I hope that next week you will get the presentation and you'll get the overview of the product we have. So we do have also ATH with low viscosity grades. These are mixture of different particle size distribution where you can get higher filling degree, and they're mainly used in thermosets application. And the Moldex are the product produced in the United States. Also, we have joint venture with an Austrian company producing MDH, magnesium hydroxide, and this is a premium precipitated magnesium hydroxide. So we have the Magnifine product. I think they're very well known, H5, H7, H10. And we do have also surface treated Magnifine grades. We do offer different coating depending again on the application. Now I'll go for the thermal management. You know, material science has been developing very fast in the last few years. Material has to be smarter, greener, smaller, faster, and lighter. But unfortunately, this makes it very complicated to solve all these issues. So let me tell you about the two facts that our study are based on these two facts. First one, electronic components are getting smaller, and they deliver more energy than ever before. That means we generate a lot of heat, and this heat must be dissipated. So why? Because extra amount of heat will affect reliability and lifetime of the product, especially in electronics. Now, the other fact, you know, polymer material, as you're all dealing with polymers, are an ideal material, are the material for the future, because you can design very efficient geometries, very integrative and complex parts. You can replace most costly and more heavy metal components, and you can have longer lifespan. You don't have the corrosion and wear off issue that you have when you have metal components. So the filler or functional filler we're adding to improve thermal conductivity are all based on aluminum oxide. We do aluminum oxide by simple reaction. You know aluminum hydroxide. It's calcined at higher temperature. You get alpha aluminum oxide and water. And we can optimize this process, so we have rotary kilns that we can control the morphology, particle size, morphology distribution, and different milling technology. As you see, post-synthesis treatment, we can tune the surface area, the particle size, where we do different post-synthesis treatment. And at the end, we can do also some surface functionalization to improve compatibility with the polymer. So these products are used as thermal conductive filler. Now, why alumina is a good candidate for this application? Because it has very unique characteristic. First one is isotropic thermal conductivity. This means heat dissipation will occur in all directions, which is around 30 watts per meter Kelvin. We have high dielectric strength, which is very important for quite a lot of electrical application where you need electrical insulation properties. We have high thermal stability. It's chemically stable, low heat of expansion. That means dimension stability of your parts will be very good. It's a white powder, and it's green material. So REACH registered, even for food contact application, it can be applied. Now let's jump into the theory a little bit. As you see here, we have to the left some values from literature. Thermal conductivity, this is logarithmic scale. This is thermal conductivity of different polymers. Most of polymer, as you see, they have very low thermal conductivity, so they're used as thermal insulator, typically, in window frame or foams or other form. And they have thermal conductivity in the range of 0.1 to 0.4. Now, you can add different functional filler to improve the thermal conduction. And in that case, I divided the filler you can add in 3 categories. First one will be inorganic fillers, this such as alumina, boron nitride, aluminum nitride, other clay, other inorganic material. You can use metal particles, and these are copper and others. And you can use carbon-based additive. You have graphite, you have multi-wall carbon nanotube, you have graphene, you have single-wall carbon nanotube. But when you talk about electrical insulation, we have to exclude all carbon additives and metal particles because you will get improved electrical and thermal conductivity at the same time. So therefore, we concentrated on our electrical insulative application, So in literature, you find a lot of equations that describe the correlation between filler degree and the thermal conductivity. So what do we have here is relative thermal conductivity versus the volume percentage of the filler. And in that case, this is Lewis-Nelson equation. They took alumina, filled in epoxy resin, and they found that theoretically you can add 64 volume percentage, which depending on the density of the polymer, it's around 88 to 90 weight percentage, and therefore you get 10-time improvement of thermal conductivity. That means if you want to improve thermal conductivity from 0.2 to 2, you have to get very extreme filling degree. So the challenge at Martinswerke was, how can we add extreme filling degree, but we keep certain polymeric characteristics, such as elastic characteristic, processing, weight, and all of these. So we did that. Instead of giving powder to our customer, we see ourselves not only as raw material supplier, we have very well-equipped lab, so we have all mixing technology, we can do twin-screw extruder, we have post kneader, we have roll mill, we can do all injection molding, we can do also all mechanical testing, thermal conductivity testing, flame retardancy anyway. So we did all the development in-house, and we wanted to understand correlation between final composite characteristic and filler characteristic. And to the left, you see the mechanical property of different compounds, and these compounds are all at 80 weight percent, so you have a constant filling degree, you have the same polymer, but you have different powders. And in that case, we took here only the surface area, BET, square meter per gram. And you see if you need high elongation at break, you should get filler with low surface area. This is logical. But then you say, okay, it's very simple. We don't need to do a high-tech development. We can get any filler with low surface area. But when you go to the right, you see the rheological properties. If you have the MFI, the melt flow index, you have filler that has very low surface area, but they have as bad melt flow index as filler with high surface area. So it's not very simple. It's not only describing the relationship between filler and polymer. It's more understanding the whole spectrum, which starts from particle design, particle morphology, particle packing density, surface treatment, and all of these factors. So we optimized all of these factors, and we came up by 4 series of products. So the first one is TM1000, which is economic product, when you need to reach not very high filling degree, but moderate thermal conductivity. Now, when you go to the 2000, you can reach a little bit more filling degree, keeping same mechanical performance. And if you need superior properties, you can go to the 3000, which is very low viscosity product, surface treated, and you can get up to 90 weight percentage. I'll show you some data later. The series 4000 is specially designed for polyamide. We get a lot of requests from automotive producer who wants to have some electric cover or parts housing with improved thermal conductivity using polyamide, and we found very good solution using our filler for this technology. So if we start for series 1000 to 3000, these are mainly for thermosets application, and therefore we divided the product according to their viscosity. So you have product with moderate viscosity, lower viscosity, and very low viscosity. That means you can add them to the thermosets. This could be polyurethane, epoxy, silicone, any thermosets, and you can steer them at room temperature without adding any additive or compatibilizer, and you can reach up to 90 weight percentage, and this material will still flow. Application mainly thermal interface material, TIM, encapsulation, resin casting, but we do also use this product for elastomeric sheets. These are thermal baths for solar panels or any other application. Battery separator could be some sheets using there. That means the target of our development, how can we make very low viscosity product, and this very viscosity product, low viscosity product, you can use them at very high filling degree and get extreme thermal conductivity. So all this measurement of viscosity you see here, they're done in the same resin, which is polyether polyol, at the same weight percentage. So you see here the advantages between the different series according to their viscosity and how much you can go high with the filling degree. These are the data we measured at our lab. So we use the TISIS technology. And again, if you talk about thermal conductivity, there are so many methods you can use, and there is no agreement which method and which data you can trust. But we compare our results to all other data, mainly used laser flash, which give a little bit higher results. So our method is very conservative, but I believe that this method, it's very reliable method. Because if you understand it, let me go through the method. So you have here two blades of the compound. You insert them vertically, and you have in between, if you do cross sections here, you see the heater. So you have a 5 centimeter heater, which gives you a certain heat flux, which is constant for a longer time. And you have two blades, and the temperature the heat flux will go through the sample. And then we can measure the delta T. So if you have the delta T, you have the thickness of the sample, you have the heat flux, you can directly calculate the lambda, the thermal conductivity in watt per meter Kelvin. Therefore, we call this method a direct method. This means you have lower chance to get more error in this method as compared to laser flash, where you have very short laser pulse and very short time of measurement, and you measure heat capacity, heat diffusivity, the density of the sample, and then you calculate your heat conductivity. So this method, giving only through plane value, and we find that in most of the application, this is more required to have heat dissipation through the sample. So if you're talking about battery housing or electrical components, you want the temperature to go through the sample, through the wall, to the surrounding atmosphere. In that case, we measure the through-plane thermal conductivity using our conservative method, and you see the beginning, the unfilled polymer has very low thermal conductivity. It's almost insulator, 0.2 watt per meter Kelvin. If you go higher to 50, 60, 70 weight%, you get some increase in thermal conductivity, but this is not very significant. What I mean by significant is still like from 0.2 to 0.9, that's 300 to 400% increase in thermal conductivity, but that's not very much. But if you reach the percolation threshold, where particles touch each other, you see that the thermal conductivity increases significantly after this concentration. So after 80 weight percentage, you will get 1.2, 1.9, 2.4, 3 watt per meter Kelvin at 90 weight percentage. And the 4, that's not commercialized yet. That's still development. But we promise that we can reach in certain polymers, depending on the thermal conductivity of the polymer and the filling degree, up to 3 watt per meter Kelvin through plane. And as I mentioned in the beginning, if you remember, we have isotropic filler. That means you don't have to take care of your particle orientation. You will have all heat dissipation, all direction very similar. Now, what does this mean? As I think Dr. Zauerwein from Nabaltec said, most of the application, you can cover them by heat conductivity between 1 to 2 watt per meter Kelvin, because that's already 1,000% higher than the unfilled polymer. So we see also the same trend. So starting by thermal conductivity 1 to 1.5, you get great or significant reduction in heat of the component. So this series you can apply in elastomer, in thermosets, and then we said, okay, automotive, polyamide, it's a very big request, so let's do work in polyamide. So we started almost 2 years ago to work in polyamide, and as I mentioned, we have in our facilities twin screw extruder, boost kneader, so we did the development in-house. We have main application for polyamide are housing, electrical connectors, electrical parts, and not only automotive, this could be LED, lighting, and many other applications. As I mentioned, when you go to extreme filling degree, the polymer polyamide is very brittle, so you have to be careful that you get good mechanical performance. So our development gives you good viscosity and good mechanical performance. So if we will go through the advantages, we see that low viscosity, as you all know, means efficient extrusion, means low injection molding pressure. So instead of using machine, using other product, other technology at 1,500 bar to make these parts, we need only 600 bar. So you have very good flowability, very good viscosity, and low pressure for injection molding. Now, the most important things, when we replace metals, we make very complex geometries. And this is the advantage of using plastic and injection molding technology. So good part filling is very important. And that's something we see because we have very fine dispersible particles. You can make very thin walls. We did parts with 0.4 millimeter and still can do very nice injection molding at very low pressure. And that's a very big advantage for this product. Thermal conductivity polyamide, you reach around 1 to 2 watt per meter Kelvin. The unfilled polymer will have around 0.2 to 0.25, depending on crystallinity of the polymer. We found that you can reduce injection molding cycle time. So in Germany, automotive, it's very popular to make injection molding. And if you produce 4 million parts per year, and you increase the thermal conductivity of your polymer, you can reduce it up to 50%. So instead of making 2 million parts or 4 million, you make 4 or 8 million parts at the same time, so it's cost reduction. Now we find also that the mechanical performance, mainly for polyamide, two things, elasticity, so elongation at break, and Charby. So we found that using our product, due to the surface treatment, unique surface treatment we use, we have very good adhesion between filler and polymer, and therefore we get very good mechanical performance for this product. I have some sample. If you're interested, I can show you later. Now here I have an example of martensiite TM4410 in polyamide 6. We have different loading between 50 and 70 weight%, and this is the most used loading to reach 1 to 2 watt meter Kelvin. You get the loading on volume percentage. It's a little bit lower or much lower because we have high density, 3.9 gram per cubic centimeter. So it's 22 to 40 volume percentage. You still see elongation at break, 5 and 4. This might not be very high, but for polyamide filled, highly filled, that's very high. So as compared to other technology, these are 300 to 400% higher than other technologies. E-modulus still very okay, because we're not using glass fiber, so we just replace all glass fiber. We get some reinforcement effect using our mineral additives, so we get up to 10,000 megapascal for E-modulus, tensile strength around 100, that's also good results, and Charby, good, you can't compare the absolute values because it depends on the method temperature, so with the room temperature 4 joule, still very okay because you have good adhesion between the functional filler and the polymer. We do also injection molding spiral flow to check the flowability of the product, and we see using our product, we get more advantages than using other available technologies, so we get almost 100% more flow at the same pressure and same condition. Now we talked about the product, we understand the technology, we understand the application, we know how we can use it. Now the customer will be afraid, aluminum oxide has most hardness of 9, it's very hard, it's very abrasive now. We can tell you, we have know-how in producing different grades of aluminum oxide, and you can optimize this property. So you can work to optimize this property. So it's unfair to describe all alumina using the word 9, because that's unfair. Because in polishing application, you have products which are very fine, which are very soft. You can use them for automotive lac, but other they are very hard and very abrasive. So we try to optimize the product that are used for polyamide, because you have extrusion, injection molding that are very wide, very fine, they're very rounded, so you will not have high abrasiveness as you will think. But for other application, when you have thermosets, when you just stir your powder into your resin, that was not the biggest issue. So we tried to optimize this morphology, and that's here very nice SEM images. People are afraid of these. These are 50 micron, corundum, very hard, having very sharp edges. But our products are based on very fine dispersible product, very rounded edges, surface treatment. So we try to optimize all of these conditions to deliver a white powder. Of course, you can measure all iron content. You can measure after coating, after compounding. We did all of this measurement. And now we're cooperating with a very well-known institute in Germany to make really measurement to measure the abrasiveness as compared, let's say, for glass fiber, 30, 60 weight percentage, as compared to other filler which has lower hardness. So we're trying to do all of this. But my message here, to describe the abrasiveness of the material using the hardness of the most hardness, that's unfair because it's so many other factors: morphology, particle size, surface treatment, and viscosity in the compound. So if you have a compound having double of the viscosity, and you're doing injection molding or extrusion, you will have much more abrasiveness, even if it has lower most hardness. So let me summarize the product portfolio for the thermal management application. We have the series 1000. We have 4 products in this series, varying in particle size, morphology. Main application, polyurethane, epoxy, silicone, and some elastomers. Filling degree is around 30 to 60 weight percentage. So the requirement here, if you want to get only 1 watt meter Kelvin, only it's still 400% higher than the unfilled polymer. Now, if you want to go to the series 2000, you can put more, keeping your mechanical and processing properties. We have the 2004 product, also for same polymeric application, but this you can use also for polycarbonate. We have many LED application, polycarbonate, where people think, okay, we can't use this one, literature say, and everyone says, you can't use little bit basic filler, but when you do the right chemistry, we were able to do that. So also for polycarbonate, we can apply. We have few running projects in Germany with polycarbonate. Now the 3000, this is very, very low viscosity grades. Of course, packing density, surface treatment, right morphology. And these products are ready to use. You get them, you put them in thermoset application, semi-conductive adhesive, gap filler, grease, and you get 80 to 92 weight percentage. That means you have homogeneous heat dissipation, 3 watt per meter Kelvin. This is 1,500% higher than the unfilled polymer. You can use them in the same polymeric application, but here it's more product choose, it's more about the requirement you need. And the specially designed product 4000, which is for polyamide application, we worked with mainly 6 and 6.6 because automotive is very cost competitive application, but we do have also very niche product application where you have other specialty product, crystalline product, high temperature polyamide, because as I mentioned, polymer, and you have an operation temperature, automotive polyamide 6, let's say 130 Celsius degrees, and if you improve thermal conductivity and you have a permanent cooling of your polymer, you can increase your maximum operation temperature. So they're using now polyamide with high temperature polyamide to replace most expensive high temperature polymers. Now here, I try to visualize few data, because you tell me 1, 2, I don't understand what does this mean, 2 watt meter Kelvin. So we took here different plates of our elastomer. One is unfilled, so you have 0.2 watt meter Kelvin. The other is filled to 1 watt meter Kelvin. The next is 2 watt meter Kelvin. The last one is 3 watt meter Kelvin. So we have 75, we have 85, we have 90 weight percentage. And this product, we took this metal cylinder, so we applied the heat source. We wanted to simulate LED. So you have LED, which generate energy. You have the thermal baths mounted, the LED mounted on these thermal baths. And then we took these metal cylinders, we heated them up to 60 Celsius degree in oven, and we put them on the top of these plates for only 20 seconds. And then we removed them. So you see here, when we made the first thermal image, we removed the heat source. And you see after 0 second, 20 second, 210 second, the cooling. Now let's check only 220 second. You see the unfilled polymer still have hot spot, and the 3 watt meter Kelvin, the isotropic heat dissipation, very homogeneous cooling. You get, even if you say it's only 10 degrees, I don't care, it's not very high, but in automotive, in adhesive, this means going to the next level, next qualification level. So if you qualify your polymer to be used at maximum 140, you can go 10 degrees more because you have this 10 degree temperature difference at permanent. Of course, that's a very simple test. It just gives you an indication. We have to do more simulation, more parts, because it's related on the power input, the convection condition, all particle designs. So that's more complex than this one, but this very simple image showing the heat dissipation. Now, as we do thermal conductive filler, we said, okay, our main competence is flame retardancy. Let's see what's happened to flame retardancy of these compounds. So typically, I think you're familiar with the heat release rate curves produced by cone calorimetry measurement. So to the left, you see we took standard cable formulation, which is blend of EVA and polyethylene, and we typically add our aluminum hydroxide, 68% as flame retardant. Now, in that case, we replace this aluminum hydroxide and we add our aluminum oxide, so martoxide grades. And in the case of 68% aluminum oxide, it doesn't give any water because the aluminum hydroxide have the endothermic degradation, give the water, dilute the gas, and therefore you get lower energy. In that case, it's dead filler. So the aluminum oxide, when you increase the amount of aluminum oxide, you should expect only reduction of peak of heat release rate. But in that case, we see, interestingly, improved time to ignition. That means you get automatically better flame retardancy when you improve your thermal conductivity. But of course, if you're having extreme filling degree, there is no space more for flame retardant, and you don't need them because you don't have polymer anymore. So if you have 90 weight percentage, you don't need any flame retardant, and you will pass most of the tests. But to visualize this, we did also thermogravimetric analysis, TGA, and this is, you see very nicely, it's improving thermal stability of the compound. So the unfilled polymer we took here engage as an elastomer, and the unfilled polymer will burn 100% weight loss. And if you add 50, 75, 85 weight percentage, you will have improved thermal stability up to 40 Celsius degrees. Now, to be fair, as scientists, that's not very fair because it's all related at the condition of the measurement. So we did only 1 degree per 1 minute. But this showing the trend. If you have high thermal conductivity, more filler in, you can improve your thermal stability. But to understand this and to calculate your maximum operation temperature, you have to do different aging steps at certain temperatures. But that's showing very good trend. Improving thermal conductivity will improve somehow to certain extent the flame retardancy of the polymer. Now to summarize, we have low viscosity products are used in thermosets, And you see here the flowability of this product, because main application will be dispensing, so you need good flowability. And you see when you do the right coating, these are same product, so same feedstock, but have different surface treatment. So if you see you have the right coating, you get the great viscosity and flowability of the product. Now the other example, we have good processability for this material in both thermosets and thermoplastic, but we have also superior mechanical properties. So you see here a sheet which is produced of 98% filler. If I tell someone this before, they say, okay, it's not possible to put 90-gram filler plus 10-gram polymer, but in that case, we have somehow, to a certain extent, flexible sheet that you can use. It's not ceramic, so still having very high ceramic percentage, but you can still call it polymer material. On the other way, you see that we have polyamide spiral flow, very good flowability. So even if you do injection molding or pressing or any method to produce your sample, you will have very good properties. Let me thank you, and if you have any question, please just ask or visit us to our table.